Join us on a fascinating journey into the world of aeromodeling, where the elusive term "thermal" becomes a key to unlocking the skies. Did you know that thermals emerge both in winter and summer? Before delving into the intricacies of the topic, it's crucial to understand how air behaves under specific conditions, giving rise to thermals. We'll start by exploring the terms stable and unstable concerning air masses. Imagine a kettle on the stove, where rapidly heated water becomes less dense and ascends, creating a continuous flow. This analogy helps grasp the instability leading to the boiling point, akin to the process of making water boil. In the atmosphere, stability arises not when temperature increases with altitude, but when it doesn't decrease by more than 5.4 F minus 14.7 degrees Celsius per 300 meters. Understanding this stability coefficient is vital, especially in differentiating between dry and humid air. The latter, saturated with moisture, alters the coefficient, showcasing the intricate nature of thermals. Discover how thermals form on warm, clear days as the sun's rays directly heat the Earth's surface. The heated air rises, creating warm air currents resembling bubbles, an unmistakable thermal. As these thermals ascend, expand, and cool, they form clouds, saturating with moisture until they reach a sustaining temperature, creating a thermal base. Learn the subtle nuances of thermals, including their afternoon decline as the sun's rays weaken. Stay mindful of cold, descending air currents adjacent to uplifting thermals, capable of swiftly bringing a model down. Unravel the mystery of finding thermals, where different terrains play a crucial role. Dry terrains favor thermal formation, offering aeromodeling enthusiasts the opportunity for thrilling flights. In the vast expanse of the flight field, the phrase "thermal" is frequently heard, yet do we truly comprehend the origins of this phenomenon and the optimal techniques to harness it for our benefit? Did you know that thermals manifest both in winter and summer? Before delving into the intricacies of this subject, it is essential to grasp how an air mass behaves under specific conditions, giving rise to a thermal. Initially, let's explore the terms stable and unstable concerning an air mass. To illustrate, envision a kettle of water on a flame where the water at the base is heated more swiftly, becoming less dense. Being less dense, it ascends in the water mass, allowing the cooler water to take its place. As the cooler water heats up, it rises again, creating a continuous current until the water enters the boiling process, i.e., it boils. This boiling process depends on the instability condition of the water when, due to temperature, the denser water mass is above the lighter one. In the atmosphere, stability is achieved not when temperature rises with height, but when it doesn't decrease by more than 5.4 degrees Fahrenheit minus 14.7 degrees Celsius per 300 meters. If the temperature descends beyond this value, the air becomes unstable. This coefficient of 5.4 degrees/300 meters is applicable only in the case of completely dry air. In the case of moisture-saturated air, the coefficient transforms into 2.8 degrees/300 meters. The distinction between dry and humid air values results from the latter yielding latent heat upon condensation of its water vapor. The caloric efficiency of humid air prevents abrupt fluctuations in ambient temperature, unveiling the birth of thermals. Let's delve into a warm, clear day's occurrences. As the sun ascends, its rays fall more directly onto the Earth's surface, heating it. However, since the Earth is a poor conductor of heat, only its periphery warms, affecting the air in contact. Heated air loses density and ascends to higher layers, forming warm air currents that generally resemble a bubble. This is a thermal. Now, let's observe the upward journey of a thermal. Gradually expanding and cooling, it reaches the condensation level. At this point, convergent clouds begin to form, saturating our thermal with humidity. While it continues cooling until matching the surrounding air temperature, preventing further ascent, it forms a supporting base. Day's progression and locating thermals. In the afternoon, the sun's rays are less direct on the Earth's surface, causing a temperature drop. As the surface temperature declines, thermal formations gradually cease. It's crucial to remember that adjacent to ascending thermals, cold descending air currents form, capable of bringing a model down as swiftly as a thermal raises it. Finding a thermal involves understanding that the sun-heated ground transmits heat to the air in contact. Certain terrains, like sandy, stony, or dry soil, are more conducive to thermal formation than low, flooded terrains or those near swamps, lakes, forests, or green fields. General observations and optimizing flights. Only a few generalities about thermals are known. They detach or originate at fairly regular intervals, with their ascending force inversely proportional to their diameter. The most favorable time to find them is between 10 a.m. and 12 p.m. When a model hooks a thermal, its speed increases significantly, directly proportional to the thermal's ascending power. It's of paramount importance for a model, whether a glider, rubber-powered, or combustion engine model, to have excellent lateral stability during spirals. Given the relatively small dimensions of thermals, the model describing circles of approximately 30 meters in diameter is crucial. We hope this comprehensive guide empowers you to achieve the soaring flights you ardently desire in the thrilling realm of aeromodeling. May the skies be your canvas and the thermals your dance partners. Happy flying!